Good to go, right? Yeah, go ahead. Hey, good afternoon, everybody. I think we are mainly focused on the operation half so far. The performances, I think, starting from this session, we will talk about what we have been doing since the HAFS version 2 goes into operations. So I think I'm going to start with the we called 2024 Hurricane HAFS real-time power experiments. I will go with the HAFS A configuration. We call it HAFS 201A configuration. We basically developed the configuration after the code handoff, and then since February, March timeframe, and then developed their system, kick off the real-time power basically in August timeframe. Still keep running as long as there's active storm coming up. But before I go to the next slide, I want to mention this is definitely a collaboration from EMC Hurricane Group, also HRD, basically HFIP community, UFS Hurricane Application Team. Yeah, please go to the next slide. So as I mentioned, this is HAFS version 201A configuration. It's based on operational version 2A configuration. We did have a bunch of additional upgrades on top of the version 2 option. Right now, we got further got the code updated to the latest version, like July timeframe version, and we got the additional vortex initialization capability upgrades, data simulation upgrades, and as well as assimilated model data and physics dynamics as upgrades as well. And another important thing is we are switching to using the new version of RTOF's version 2.5 input data. So I will not mention everything in here, but I will highlight a few important upgrades we made into this version 201A configuration. Next. So this is one of the important upgrades we made for this hurricane season real-time power experiment, which is the vortex initialization improvements. I think it's basically from John Hoon. He further improved the central pressure adjustment procedure in VI. So you can see in the slide, the Vmax for this specific cycle matched the observation pretty good, but the central pressure have a huge difference over there. So this is basically trying to adjust that issue. We did some retrospective test with this one specific change. You can see we do got the improvements in the intensity scale, especially that can be seen in the central pressure as well as the Vmax. Yeah, cool. Another important one is the 3D IAU capability. This is developed by Xu. I think this is something, another thing is this is a storm following 3D IAU capability. I think this is new, basically. Even in HWolf, we does not have this capability. This is a collaboration between EMC and the OU group as well, basically Xu coming from OU group. And I think we implemented this capability. We did some tests, and you can see here showing very good improvements for the initial intensity for Vmax, as well as the Vmax intensity scale improvements, almost all the data types here. Next. And then we also have another collaboration with AER and DTC, working on actually bringing other cloud overlapping necessary from HWolf world to HAFS world. Again, you can see here, this is for 2023 Atlantic storms here. You can definitely notice there are not much overall tracking improvements is kind of neutral, but you can see some intensity improvements here. Next. And then before we kick off the real-time power experiment, we also ran go past 2 years. So this is an overall performance for 2022 and 2023 storms. Again, you can see there are some healthy tracking improvements over there. Intensity-wise, overall neutral to improvements as well, especially not only shorter forecasting time, but also longer forecasting time. Even for the rapid intensification metrics, you can see some improvements for almost all lead time, but sample size is very small. Next slide. And again, so once we finalize everything, we basically kicked off the real-time power experiment on August 1st. We actually run all the storms, all basins, but in this talk, I'm gonna focus on the Atlantic Basin for all the storms so far we have finished, which is 1 to 18L. So this is the first set of experiment configuration performance stats I'm checking against operational HAFS version 1 and version 2. Basically, version 2 went into operations July 16th. So basically for Hurricane Beryl, this is version 1. So that's why if you hit the next slide, it will shows the clean comparison against the parallel version, which XA versus version 2A. So again, this is for all the storm cycles we have so far for the Atlantic Basin. You can see we have some 5 to 10% improvements for the track. Intensity improvements, we have a day 4, day 3 improvements, which is 5, sometimes reach to 15%, but we got some degradation at day 5. You can also see we actually improved the radius of 34 knots wind, as well as the radius for maximum wind area as well. So next. So after looking at the overall stats, I'm going to go through a few storms here. Starting with Hurricane Helene here, you can see Operation HAFS and Parallel HAFS doing a great job in track. I wouldn't complain this track. This is a fantastic track forecast. For the intensity, you can see Operation HAFS have a few cycles did over-intensify the storm, but majority of cycles did quite well. Parallel HAFS I would say overall slightly better than the Operation HAFS. Next. So this is one I think was brought it up yesterday or the day before. This is an initialization problem. I think I mentioned a few times already. So with the 3D IU capability here, if you hit another click here, I will highlight the storm structure over there. There are some issues in the Operation HAFS. You can see those weird fields, sea level pressure field as well. But with the Parallel HAFS, it's much improved at hour 0. Again, this actually propagate into focus hour as well. So I would say hour 6 is slightly better as well. Next. So also compared the Parallel HAFS against the TDR observations here. I think this is from John Hong. Again, the middle column is from Parallel HAFS, the right column is from TDR observation. The storm structure, the maximum wind distribution matched very well. You probably will argue probably the model got the storms a little bit smaller than the observation, but I would say it's overall pretty good. Next, maybe 2 click. Yes. Then another important thing, I think for Hurricane Helene, we all know the precipitation is a big issue for Hurricane Helene. We did cherry-picked one cycle, and we actually checked a few cycles. Parallel HAFS, even Operation HAFS did quite a good job for Hurricane Helene. If you hit another click that highlights the high precipitation area, you can see the pattern distribution. Even the maximum value are very close, I would say. And maybe a little bit underestimated the overall precipitation, I would say it's already pretty good. Next. So to Hurricane Milton, again, Hurricane Milton, I think both Operation HAFS and Parallel HAFS did quite a good job. There are parallel, say a few cycles, earlier cycles, the track was a little bit left bias, but after that, pretty good. And if you hit the next slide, I will basically select out another hit, please. I will select one focus hour to look at more details about the storm structure if you hit next. So this is for focus hour 16, and again, this time the model simulated storm size is actually larger than the observation. So it varies a little bit storm by storm, cycle by cycle. But I want to draw your attention if you hit another one. You can notice actually in the bottom right panel, you can see the concentric eye wall over there. You can arguably also see that feature in the model simulation as well. If you hit like there, this is for model simulated SSMLI 37 gigabyte brush temperature as well as 91 gigabytes brush temperature. You can also see the storm structure matched pretty well with the observation. One more hit, that's the azimuth average storm structure. You can also notice the concentric eye wall or double eye wall structure over there. Next, please. So talking about the ocean coupling or the ocean response for Hurricane Milton here. Again, this is an initialization, ocean initialization for HAFS coming from RTOFs. Again, you might notice actually the intensification phase of the storm is basically passing a warm high OHC area as well as a loop current. And interestingly, before in manifold, it also passes a low OHC area that actually corresponds to a weakening phase. If you hit next, and then that's our 12. Go ahead, we'll go our 24. Next, another hit. Sorry about that. And 36, 48, 60, 72, and 84. That's the one you can see that low ocean heat content area before mid-landfall. The actual HAFS forecast did quite a good job. Parallel HAFS did an awesome job here in this cycle. So if you go to the next slide, I will basically, this basically what we have been doing for the parallel HAFS, but we are keep moving forward, doing additional experiments. So we didn't want another parallel or another actual experiment by adding ocean data simulation capability on top of the HAFS parallel experiment configuration. I think Hans already mentioned some of this capability in her talk, but this is just a clean comparison for 2024 hurricane in the Atlantic Basin. I think 6, 7 storms we already finished. So it does show with the ocean DA capability, we can further improve the track as well as the intensity. If you hit another click, that's a skill space wise, you can see those improvements. One more hit, please. That's the improvements in the Vmax bias as well as radius for maximum wind. One more. Thank you very much. And then this is another additional experiment we have been doing for the downstream testing for the RTOFs version 2.5. So that is the new version RTOFs going into operations potentially next March timeframe. So that's why we need to do these tests. Overall, I would say the impacts are kind of neutral or neutral to positive for both operation HAFS as well as real-time power HAFS. Yeah, next. And then this is quite interesting. I'm not sure how many minutes I got. 4 minutes, that's good. So this one is an important one. I think this is the additional improvements we are looking forward to. So the XR is the one we mentioned, the parallel HAFS with the new RTOFs. The new experiment I'm introducing here is the EX2. The only one difference added here basically is the wave number filtering capability, which existing in HWF world, but not yet in HAFS world yet. I think Zhonghu, Yonghui, and working together with our DA team here, enabled capability for HAFS, and we actually conducted majority of the 2024 Los Angeles storms here. One thing you can notice, you do see some good, healthy improvements for the first 3 days intensity forecast. That's one of the aspects HAFS is behind HWF for the earlier proximity time. So this does signal saying we are moving to the right direction. I also list here hurricane barrels. Basically, this has a larger impact when you have strong storm, basically. So you can see we have some good improvements for hurricane barrel, Helene here as well, clean improvements of there, hurricane Kirk and Milton. So again, this is something we will continue working on to improve it. Next, please. And then combining 2024 and all the 2 years retrospective tests together, this is 3 hurricane season stats, basically parallel HAFS versus operation version 2 HAFS. Next click, it will show you skills. Basically, you can see about maybe 5% improvements for the skills for track, all improvements over there. Okay, that's my second to last. Okay, so you also see the consistent improvements for the intensity as well. So rapid intensification stats improvements as well. One more click is the IR performance diagram. You can see the Sion part is slightly better than version 2 HAFS over there. One more click, that's my last slide. It's basically a kind of summary and future development for HAFS. I probably will skip it.
All right.
Thank you very much.
So, question at the end of the QoS sessions at the end. And the next talk, Andy will talk about HFIP real-time experiment. And Andy worked at HRD before he recently joined the EMC. Andy, go ahead.
Okay. Oh, wait, now it is. Okay.
All right.
Well,
I'll give it a shot.
Apparently it's working now.
Good afternoon, everybody. Thank you for coming. Like Zach mentioned, I was at AOML and HRD. Now I'm over at EMC. So I'm going to be talking about the HAFS 2.01b real-time parallel experiment. This is definitely a team effort. I'd like to thank Jung-Hoon, Wego, and Chunkai, and Lou, who all helped kind of run this during the times when I was out, doing hurricane flights, things like that, and certainly everyone that's contributed to the HAFS development there. So basically, it's based off of the HAFS version 2.0 with some kind of the more recent upgrades to the UFS weather model. There's a couple key things that we've added for this year's experimental real-time version. The big one is in the physics. We used the TDK convection to try to get some diversity compared to HAFS A. We made a couple little changes to that, some things with the scale awareness and also the detrainment that Jung-Hoon worked on to try to improve some of the biases. And also we did one other key difference this year is ocean coupling is using MOM6, whereas operational HAFS B is using HICOM. And we used some different mixing options that Hoon Suk provided to try to get things a little bit different from HAFS A. And a few other key things that were changed were in the initialization, the improved DI for the pressure bias, cloud relocation, and also that 3D IE that Ben mentioned. And you'll see that this had an impact on the initialization improvement. We're running these 4 times daily on the JET reservation. So I'd like to thank all the JET admins for keeping that system up and running for another year. And then we've also been running on HERA for sort of as a backup or, for cases when we had more than one storm out there. So I'll be showing, start with showing some overall results. I'm going to be using Sarah Ditchek's group package where you can kind of see the consistency metric and whether these results are robust. So this is for track. So here we have our operational and HAFS A and B, and then the experimental. So magenta is the basically what I'm talking about here, the experimental HAFS B. We're using the operational HAFS B as a baseline. So you can see we actually did have some solid marginally to fully consistent track improvement. If you kind of see there's a mixed bag in some of the cases, like Ernesto was very solid and consistent improvement, whereas for Milton, we saw some degradation, and I'll look at that case in a minute and show what was going on with that. For intensity, the big thing is you see this huge improvement in short term, and that's with those 3 IU and the improved initialization. Unfortunately, that's not translating to the day 1 to 2 improvement. It kind of immediately jumps back to where it was. So that's telling you that we're probably not fully, in this current version, fully there with the improved DA. I think some of what Ben was showing with the increments and the filtering might help. And then as eventually we need to get away from using the GDAS covariance. So I think once we do those things, this improvement will hopefully translate down the line. But we still did see some overall improvement, especially in that longer lead time, fully consistent. So overall was doing well here with the changes in the physics. Now, one of the key metrics is this HFIP RI metric. Basically, this is basically some of the definition that I think Mark DiMaria and others came up with, where if one of the constituent models or the storm itself undergoes RI during the period, you count it as RI, and then run your verification for that. And we have the HFIP baseline and goals there, and the gray and black dashed lines. And you can see that pretty much all the HAFS models, especially HAFS B, were pretty close to our goals out to day 3. Maybe a little bit larger or longer leads. Experimental version was sort of comparable, maybe a little bit more of a negative bias at early leads. So that's something we did try to adjust for some of that in the TDK, but I think there's still a little bit of a negative bias that we might have to work through for some of these RI cases, but pretty encouraging overall. This is something we've been looking to improve because I think some work has shown that so far HAFS RMW skill is not really that much better than climatology or basically like a statistical model. So we want to work on improving that. The RMW bias for the experimental version here is improved over the operational version. So that's good, a little bit better. But R34 is still a little bit too negative. So that's something we'll have to work on. So let's start looking at a few of our case studies. Hurricane Milton is one. This was obviously a very impactful one. So we have here the tracks for operational on the right and then experimental HAFS B. So the cross-track error was lower for the experimental version. It was closer to Yucatan. The landfall point was pretty much right on Sarasota County, which, whereas the operational version was kind of, it was a good track forecast, but it was maybe a little too far north. Some of the cases were Pinellas County or, right in Tampa Bay. But there was a little bit of an issue with the speed. You can see kind of see it. There were a couple of the cases were way too slow in bringing the storm into Florida, and we'll look at why that was in a second. For intensity, this is one where the RI was predicted quite well. I think if you probably look back at something, maybe this meeting 10 years ago, the idea that you could get RI scale like this is pretty unfathomable. And certainly, this translated to the NHC errors being very low. And this was a well forecast case. Maybe just a little bit too late. The RI happened a little faster, but overall, it was quite well predicted. And that's a function partially of the storm structure. So what I have here is the model and observational comparison. So on the top row is basically horizontal, or top row is the model, bottom row is the P3 data from the same time. You can see basically the HAFS-B experimental version was able to predict this tiny pinhole NRI and the eye wall replacement cycle that was ongoing, which is pretty remarkable that 3 days out you can pick up that kind of structure. Maybe it was a little bit, if you compare the vertical reflectivity profile, it looks like maybe the ERC was a little bit further along in the model than OBS, but the fact that it was picking out this process is pretty good. But one thing, like I said, the one issue we did note was that a few of those early cycles, if you look at the bottom left, had a real notable track bias, and it was mainly a long track. It was too slow to come into land. And the reason for this was that the outer nest of the storm had too strong a representation of 93L, which was like a frontal wave, another invest that formed out east in the Bahamas, and that interaction seemed to basically unrealistically slow down Milton in a few cycles. So this might be one case where something like the basin scale that I think Lou's going to talk about next, where you're getting those multi-storm interactions, would probably hopefully do a better job of handling that. So it might be interesting to sort of combine the physics that we did here with the basin scale and see if that leads to a better result. OSCO is one. I think Philippe Papin mentioned this one. A lot of models struggle with it in the pre-genesis phase, basically not even showing a reflection of the storm. Once it did get picked up, the tracks were generally pretty good. The experimental version did a little bit better than the operational version in kind of recurving it rather than stalling out over Cuba. The pre-genesis forecast, like I said, completely missed the intensification. Not very, almost like a Otis type case, but in the Atlantic. After Genesis, the forecasts were generally pretty good. The one thing we did see, if you look at that plot on the left, there was a high bias in intensity, where it was kind of blowing it up to a major hurricane. That wasn't reflected in the best track. Although I would note that there was this right before landfall. Unfortunately, because of the proximity to Cuba and the mountains there wasn't recon for the last several hours prior to landfall. But a Sahara overpass did suggest that maybe there were some higher winds there, closer to 100 knots that might indicate the model was closer than we think. I know there's concerns about some of the, at least uncertainty about how reliable that is, but, depending on what that looks like postseason, this forecast might look a little bit better than it does right now. This is one, arguably the most impactful case of this season. The track forecast is really about as good as you can hope for. Maybe again, a little bit of a slow bias in some, and a couple cycles were too close to the Yucatan, which led to a little bit of volatility in the intensity, but overall pretty much nailed the landfall point just east of Tallahassee there. And then also the track up into Georgia and the Carolinas. The intensity again is pretty forecast. The one thing is that the RI was started a little bit too soon in some of these, and we'll look at why in a minute, but overall it was again pretty well forecast. Looking at the model and observational comparison, again, the top is the model, bottom is the OBS, and in this case, maybe it was a little bit too quick to form the inner core. So Milton, that inner core sort of got going right away with really not much interruption from dry air. And Helene, maybe because of the origin of the storm, it was a gyre that kind of spun up and ended up being a little bit broader in reality. It took a little bit longer to get going than the model was suggesting. And the other thing that we noticed was that if you look at this, is on the left here is an 18-hour forecast from one of the HAFS-B, and then on the right is the corresponding analysis. This is right when it was kind of going through the Yucatan Channel. And you notice there's a much bigger dry slot kind of coming off the Yucatan there in reality, and this wasn't really picked up a day or so out. And so I think that was a little bit of the cause of the high bias. We saw this a little bit also with Beryl and a couple other cases this year. So that's been something, maybe a bias that we'll need to look up in the model is, or the DA is, these dry slots and how they get into the core. So in reality, this kind of delayed RI by maybe 12 to 18 hours. But in terms of impacts, because I know this is one of the big focuses of HFIP, and something I want to think about more going forward is what are the impacts? And for this Helene case, really the impacts were very well forecast. You look at the left there, you have the predecessor rain event that caused so much flooding and devastation in the Carolinas. That was well forecast. Look at the top, the large wind field. Basically, they created a massive surge event all up the west coast of Florida, including Tampa. I was on the P3 flight when it was kind of due west of Tampa there, and I was just amazed at how far away from the center we were finding hurricane force winds, and that led to a massive surge event. And again, well forecast. The outer bands, the tornadoes. I don't think there were some of those. Obviously, Milton was kind of the one that really set the standard for that. But that was well forecast by the model there. And then the other big one was the inland wind. I'm on a project where we're looking at these inland wind gusts, and we did some real-time products, and you could see this model is predicting the hurricane force gusts well up into south central Georgia, which I believe verified, and maybe then some. So the model did a good job of forecasting all these hazards. So then the question becomes, how do we hone these products and communicate these things and make it consistent with our forecast going forward. So in conclusion, experiment has showed promising skill relative to the operational version for track and intensity with some fully consistent improvement at days 4 to 5. We saw notable improvement in the initialization thanks to 3D IAU and some of the VI changes that were implemented. But unfortunately, it's not really translating to that 1 to 2 day forecast lead time yet. So I think that's something going forward we really need to look at, because that's sort of been one of the areas where HWRF is still just beating HAFS, is that 1 to 2 day forecast range. So once we can get to that point, I think we'll be in good shape. And so the individual cases were sort of highlighted the strengths, but also areas of improvement. We got the RI was well forecast in both Helene and Milton, but maybe a little bit too early in Helene. So getting that dry air entrainment right is going to be important. And then Oscar was one where we just missed it completely, maybe due to GFS initial conditions or what, just bad DA, I don't know. But then obviously was able to intensify it after. So I think overall message is that HAFS-B in this experimental version has a lot of promise and skill for RI forecasts. I think introducing these physics changes will hopefully allow us a pathway for diversity with the HAFS-B, and as well as the basin scale version that Lou's going to talk about next. And certainly improvements are needed and ongoing, so we can improve relative to HWRF, eventually retire those legacy systems, and thinking a few years down the line, I think ensembles and incorporating all these sorts of changes into an ensemble system is going to be the way to go. So that's all I've got.
Thanks, Andy. So Andy, you save us like 2 minutes. We are caught up with the schedule right now. And I guess the next 2 talk will be online. Lou, are you there?
Yes, I am, John.
Okay,
and I apologize.
And Lou, would you like to try sharing your slides? That might actually be easier if
You think?
you have them open.
I do. Hang on one second.
Okay, so Lou Graham from HRD, he is going to talk to us about the HAFS-M real-time experiment.
I am. And a quick apology that I'm not there in person. Jumping ahead to the summary. Whoops. I had intended to be there in person today, but a health issue cropped up. So apologies to all the folks that I was hoping to see face to face. Hopefully I'll get the chance to see you tomorrow. So today I'm talking about the HAFS multi-storm configuration, HFSM or HAFS-M, also known as HAFS basin scale, in reference to the HWRF basin
Lou,
scale.
can you try to hide that little window in the lower right? Is that on your screen?
Oh, this one? Yeah, that's
Yeah.
actually from Google Meet, unfortunately. I think if I get rid of it, I might disconnect from the meeting, but hopefully that's good. So I wanted to acknowledge, thanks, Will. I wanted to acknowledge all the folks that put a lot of hard work into this. There is one person whose name isn't on here who has since left NOAA and CMUS, that's Mucha Ko, but also a great deal of hard work from Bill Ramstrom, doing the development on the moving nest, and also some optimization work during our real-time experiment this year. And of course, Guiding Lights, Gus, and Gopal for a lot of this work, and Andy Hazelton too, who is an excellent person to bounce ideas off of. And I say with lots of help from the EMC Hurricane team, which now, of course, includes Andy, but also a number of other folks, including John Binio and other folks. So thank you. Okay, now if I can advance the slide, there we go. So we'll take a look at the multi-storm basin. What is it? I'll take you through some preliminary seasonal results from our real-time experiment. So far, we have pretty much completed the 2024 season, but I'll be showing results through 2 weeks ago. So not yet including Raphael or 19L. And we'll look at a couple of case studies that show some opportunities with the system and also some challenges. And then I'll talk briefly about what we're going to be doing, hopefully moving forward. Can everyone hear me okay, by the way? Hopefully. If not, let me know. So this is the outer domain for the HAFS-M real-time experiment that we used this year. Right now, you'll show that it has 2 moving nests outlined. One is for Debbie in the Atlantic, another is for Carlotta in the East Pacific. An interesting note, this is the 850 millibar winds. You see the streamlines and the barbs. So there's actually a suggestion that there's quite a bit of interaction between O4L and O3E, even down at 850 millibars, despite the intervening land. We'll see that might actually have played some role in some of the more positive results I'm going to show. This, for comparison, is the operational HAFS-B, which is the storm center domain for 97L, what would become Debbie ultimately. It's just a way of comparing the size of the domain, which we think might be important for some of our results, and also the fact, obviously, that there's just one moving nest. So the HREX 2024 for HAFS-M allowed up to 3 moving nests. So this is actually a slight tweak to the configuration, just showing a period when we had 3 moving nests. It's the same 2 storms I mentioned earlier, Carlotta and Debbie, in the Eastern Pacific and the Western Atlantic. And you notice 95E Daniel briefly appears for the first few forecast hours. And you'll see its moving nest. We're looking at the relative humidity in the mid-troposphere. You'll see it actually reaches the edge of the domain during the running of this test. Okay, just a summary slide of all of the blocks that are included, all of the groups of forecasts. You'll notice that each block generally includes more than one storm. You'll also notice that there is one block that with Helene, John, and other storms, which actually required 3 blocks. The reason for that is that we did find an issue, which we're actively working on. So those 3 blocks represent 3 forecasts, which could not complete. And that is, as you'll see, 3 forecasts out of approximately 600. So not a bad percentage, but we did want to be upfront about that outstanding issue. This is another slide that's just meant to convey a very broad piece of information. I'm not going to talk about this at any length, but this is produced by Sarah Ditchek's Groot package. If you haven't looked into it, I highly recommend it. Wherever you see green here, that is a suggestion that that particular metric shows improvement in the HAFS-M real-time experiment versus the operational HAFS-B, so HFS-B. Version 2. And so there's a fair amount of green here. Dark green represents significant improvements. You notice also, by the way, on the left-hand side, which is the initial, the analysis time, there's a fair amount of orange and red. So we'll talk about that briefly. This is a close-up of the consistency scorecard for all of these metrics: track error, maximum wind, minimum pressure, 34 knot, 50, 64 knot radii, and radius of maximum wind. You see, in general, the consistency scorecard from Groot shows fairly significant improvement across a lot of these metrics. And again, I want to emphasize this is comparing the multi-storm configuration based on HAFS V2, the operational HAFS V2B, not with the experimental version that Andy described in the previous talk. Looking at some statistics in skill space, you see we have some fairly, what look like substantial skill improvements in track, mean absolute error, and in VMAX, MAE as well, again, comparing with HFSB. For most lead times, the one exception, the one very notable exception actually, is at the analysis time. So again, we'll talk briefly about that later. Similar statistics for P-min, generally good improvement, except at the very longest lead times, and again, at the analysis. And just to summarize some of the structure metrics, this is the R50, mean absolute error skill. Looking at individual storms, we'll see that the nice results I just showed you are largely, not completely, but largely the result of contributions from 4 or 5 of the active systems this year. And in particular, you notice Beryl, Debbie, Ernesto, which was a real star for the HFXM, as well as Leslie and Oscar. We did have some improvements for Milton and some of the other systems, Helene in particular, but not as notable as it is for those. It's worth pointing out, by the way, that Debbie and another system in the East Pacific, as I just mentioned, Carlotta, were active at the same time. So both strong systems during that period. And Kirk and Leslie were actually both active at the same time in the Atlantic and were very likely interacting with each other, possibly in more than one way. So you notice that there's some slight degradation apparent in the forecasts for Kirk for track, roughly corresponding with the improvements in Leslie. This is the consistency metric for track. So as I have come to understand it, the consistency metric where we see a block of green that is longer than a couple of boxes, we're seeing fairly sustained, consistent improvement in one model over the other. And you can see that with Beryl, to a lesser extent again with Debbie, Ernesto, Helene, Leslie, and Oscar late in the season. Also at long lead times, interestingly, in Milton, although we also see periods of relatively sustained degradation in early Kirk, mid-Kirk, and also in Milton. Looking at VMAX, again, a promising story, particularly for Beryl and Leslie. You notice, by the way, that I've highlighted some of the East Pacific storms which did have moving nests in HAFS-M during the course of the experiment. So Alita was active at the same time as Beryl, and there was also an invest for a period of time during Beryl's activity. And again, Debbie with Carlotta, Daniel, Amelia, and Fabio, which is a fairly active period. And of course, as I mentioned, Leslie and Kirk interacting with one another. And again, the consistency metrics, a very nice story for Leslie at all lead times except 0, which is intriguing. So that's for VMAX. Pressure, a pretty similar story. We actually see some greater degradation in pressure at hour 0 and also some degradation in the minimum central pressure for longer lead times in the case of Beryl and Kirk. And we have some suspicion that issues that have already been highlighted here and may already be fixed, in fact, in the version 2.0.1 version of the HAFS code base might actually help us address some of those issues. And again, the consistency metric. Notice, by the way, that we have suggestions that Milton's minimum central pressure here showed degradation. The consistency metric, though, only shows one brief period for Milton when there was consistent degradation for a period of 3 forecast periods. Looking at a couple of particular example forecasts for Milton. So this is one where a lot of the operational and experimental systems missed Milton's initial RI. This was at hour 36 in this forecast. It was initialized on October 6th at 12Z. The HAFS-M, which is the downward pointing blue, dark blue triangle in this pretty complicated graph, generally, other than missing that RI, tracked the intensity pretty nicely. And by the way, you'll also notice the case that this is similar to what Andy was looking at earlier with Milton, the HFXB, which was the version 2.0.1b experiment, did persist at a fairly long period of higher intensity. And taking a look at the tracks, we can see that that was, as Andy pointed out, the result of a long track error. Generally, though, a nice clustering of tracks. Unfortunately, at least in this particular forecast case, HAFS-M didn't show much improvement over the other operational models, global or hurricane, or experimental models in terms of the left of track bias. The one notable exception here, as has been pointed out, I think previously, was the CTCX. Here's an example of the initialization issue that we think we've identified. So this is a minimum pressure for a forecast the following day, about a day and a half later. And you'll notice that for the operational HAFS-B, which is this sort of brick red downward triangle, central pressure was initialized straight on, directly on the best track estimate of minimum central pressure, whereas HAFS-M was actually initialized at a much higher pressure, so a much weaker system initially. A surprising thing happens, though. HAFS-M actually rebounds fairly quickly and begins, you don't see the best track here, but it actually tracked the best track fairly nicely in terms of minimum pressure from that point onward, whereas there was a spin up in the HAFS-B. And coincidentally, you notice the HFX-B managed to get the best of both worlds. So it was both initialized right at the minimum central pressure, according to best track, and also tracked it for the first several forecast periods. Okay, so we have a lot of configuration options with HFX-M, with HAFS-M. Here is a case from last year showing 4 active systems in the Atlantic. And you can see them on the right-hand side, including one which dissipates during the course of the forecast. That's GERT, which just disappeared. Looking at the mid-tropospheric moisture, by the way, you can see likely significant interaction, at least at that level. For example, between
we have 2 minutes.
Okay, thanks. I'm on my last slide. So to summarize, HREX this year was able to allow from 1 to 3 active storms. We had an average of 2.1 storms per forecast. We were looking at a domain that allowed initializations between 120 west and actually, I think we went down to 25 west from, it says July, but we actually began running in June, and we are still running. 628 total storm forecasts. So if you do the math, that's approximately 300 runs of HFX-M. About 40% of those, by the way, were intensity of a tropical storm or tropical depression, and 75 were actually initialized as invests. So we were having the opportunity to do up to 3 storms at once, gave us the opportunity to model a lot of weaker storms as well as the stronger ones. Upcoming work, we're looking forward to tuning the system, making it more resource efficient. Looking at the initialization DA issue, one of the big tasks we have this winter is harmonizing the HAFS multi-storm workflow with the version 2.0.1 code base, and we have some hopes that that actually might allow us to quickly resolve those initialization issues. We'd like to stratify the 2024 results by number of storms, and in order to contribute to that ongoing research, we'd actually like to do 3 and 5 storm retrospectives for 2021 to 2024. There will be a presentation at AMS Annual touching on this by Gus. Future work, as Bill is going to talk about tomorrow, Bill Ramstrom, we're looking at multiple moving nests within the global domain. We'd like to do continued fixes and performance improvements. As a consequence of harmonizing with v2.0.1, we're going to be coupling with MOM6 and therefore using the RTOF's v2.5 initialization. And we're also looking at the possibility of doing disturbance tracking. So as a way of maybe using the system as a tool for Genesis. Again, research with this system focuses on storm-storm binary interactions through the ocean, what are called remote storm interactions. You can see Gus has had a couple of excellent papers on that. And a particular area of research of mine, energy redistribution between storms in the multi-storm system. And ultimately, research and development, we'd like to be looking at cumulative precipitation. Having a fixed outer domain makes that particularly easy. We're very interested in attribution, where we see improvements, where is that coming from? And we'd ultimately like to see HFSM used as a tool for optimizing DA and HAFS. Thanks.
Thank you, Lou. Hi, Clark. I see your camera just popped on. Can you do a quick mic check?
Yep, can you all hear me?
Yep, can hear you just fine. Also, would you mind sharing your slides? We're having issue with non-Google slides at the moment.
Sure, I can do that. Let me get that set up here. All right.
Thank you.
Got that. Let's go into slideshow mode and make sure everything looks like it's good on my end. Good over there?
We can see it just fine. I think Zach wants to officially announce you, so go ahead, Zach.
All right, thanks. Yeah. And so our next speaker is Clark Evans from GSR, and he's going to talk about the tropical cyclone forecast using MPAS DICOL. Thank you.
Great. Thank you, everyone. And sorry that I couldn't join you. I've had this nasty habit of getting sick on all of my travels, and the last one a couple of weeks ago has left me and my family sick. So greetings from sunny Colorado. I'd like to acknowledge a lot of people here in GSL, namely Janet Derrico, Christina Holt, James Kenyon, Sam Trahan, Kai-Yi Wong, and all of our physics and model developers for their significant contributions to our presentation here today. So our work is motivated by GSL's Grand Challenge. Historically, GSL is best known for its regional modeling efforts that have entered operations, such as the RUC, the RAP, the HER, as well as Rufus, which is on the possible pace toward transition toward operations. However, we're looking at trying to deliver actionable global storm scale prediction and environmental information through advanced technologies to serve society. And so expanding our focus from just regional modeling to global modeling, we need to continue to push our modeling systems, our physics, our workflows, our data assimilation for other meteorological phenomena beyond those that we would see over the CONUS, including tropical cyclones. And we're attempting to tackle this grand challenge utilizing the model for prediction across scales, or MPAS, motivated in large part by the significant issues seen with Rufus in the FV3 dynamical core over the CONUS for deep moist convection forecasts during the warm season. And so for HFIP, we've stood up this regional MPAS forecast system based off of the version 8.1 code that was the current release as of the beginning of the project. We're at 3-kilometer horizontal grid spacing with 80 vertical levels. We're utilizing GSL's physics suite, which I'll go into more detail about in just a moment, developed through Rufus version 1 with very few modifications. A lot of our effort was spent porting those physics into MPAS in the standalone model so that we could begin running these forecasts, as well as other real-time tests here at GSL earlier this spring and summer. We initially planned to have 2 configurations, one without a convection parameterization and one with the Grell-Freitas convection parameterization. However, in our real-time CONUS tests, we've seen no differences between the two at storm scale resolutions. And so we've focused on a single configuration without convection parameterization here. And note that there's no atmosphere-ocean coupling. We hope that as MPAS dynamical core is potentially brought into the UFS within the next 2 or 3 years, that will open up venues for us to consider coupled ocean modeling with MOM6, but we're not pursuing that in the standalone MPAS configuration at the moment. Our forecasts are cold started from the GFS, so we do not have data assimilation in our system as of yet. We are doing soil surgery with wrapped soil conditions over North America. We're doing these forecasts twice per day at 0 and 12 UTC, extending out for 5 days. Looking toward a future where MPAS is brought into the UFS, we've developed a workflow called the MPAS app, utilizing the unified workflow tools. This starts with executing MPAS, post-processing through MPASIT, a tool initially developed at NSSL, feeding that into UPP for final post-processing. And then we use the GFDL tracker to obtain our track forecasts and GSL's internal pie graph routine to be able to create graphics for the web. Our physics suite is, as I noted, that which GSL has been developing for many years. land surface with the RUC land surface model, surface layer, boundary layer, and shallow cumulus through MYNN. We have our unified gravity wave package for drag. We also are using the RRTMG radiation scheme, although we do not actively develop for that one. And then we're utilizing the latest version of the Thomson-Eidhammer Microphysics for Operations, or TEMPO package, for which Anders Jensen is our lead developer here. So all of the people indicated by stars are active developers within our lab. The MPAS app workflow is based off of the Unified Workflow Tools, or UW tools. We use this to help streamline configuring and executing our MPAS experiments. So I have a diagram over here on the left, which is small for my screen, and I'm sure small there as well. The details are not that important in terms of what's in the graph, but it starts out with this YAML-based model configuration file or set of files that feed into this Rocoto-based automation, and then ultimately the unified workflow drivers to run different parts of the model. So for instance, preparing the GRIB files, creating initial and lateral boundary conditions, and then running the forecast. I'll refer everybody to Janet Derrico's poster at the Summer WRF MPAS Users Workshop for more details about this MPAS app, which we are working to continue to develop, not just for HFIP, but for our regional and our eventual global MPAS real-time experiments in GSL. So in terms of what we've been able to do for HFIP this year, it's roughly Francine through Oscar. We have about 70 real-time forecast cycles. We are working to run parts of Debbie and parts of Beryl in retrospective mode. And we tried to turn back on our system for Raphael. And if TD19 continues, I hope that we'll have a few forecasts for that. But generally speaking, our best set of forecasts is Francine through Oscar, with a few exceptions. Isaac was challenging because it was on the far northern edge of our forecast domain. Patty was missed largely because it was out of our forecast domain, and we have a couple of cases that were partially in, partially out of our forecast domain. Now, in terms of forecast verification, doing matched verification, I have track here on the left and intensity mean absolute error here on the right. The official NHC forecast is in the blue in both diagrams. Our MPAS forecasts are in orange in both diagrams, HAFS A and B in orange and red respectively. On both, GFS version 16 on the left in purple, and decay ships and LGEM in purple and brown respectively on the right for intensity. Our track forecasts are quite good, especially out through 72 hours, competitive with the NHC official, as well as the HAFS A and B and GFS. A bit more degradation as we get to the longer forecast lead times, particularly 120 hours. These are dominated by Gordon, Kirk, and Leslie out in the central Atlantic, recurving storms, all of them. However, for the cases closer to the CONUS, particularly Francine, Helene, and Milton, we had exceptionally good track forecasts at all forecast lead times. And I'll show an example of Milton for that in just a moment. For intensity, with no data assimilation, our forecasts at 12 and 24 hours are perhaps not quite as good as they potentially could be. But then by 36, 48, and 72, even to 96 hours, they're quite good and very competitive with both the NHC official as well as HAFS A and HAFS B. We do see a little bit more degradation as we get out to 120 hours. That's primarily Gordon. Our forecasts struggled with the intensity evolution of Gordon at those longer lead times. We have some digging in to do postseason to look at why it was struggling with these recurving storms and why it struggled with Gordon's intensity in particular. But let's take a look at Milton, continuing the theme of evaluating Milton from this session so far. The black line here is the best track, and the different colors are our forecast cycles every 12 hours. The lighter blues are the earlier, and the purples are the later ones. After this first forecast here that was a bit further north in the central Gulf of Mexico toward the Tampa Bay area, our track forecasts were very tightly clustered in space, and given the clustering of the 24-hour or 12-hour position markers along those tracks, very tightly clustered in time as well. Very close to the best track with ultimate landfall south of Tampa, St. Petersburg. And so if we take a, intensity. Excuse me. I was gonna show a little bit about the actual statistics for the track forecast. But before I do so, taking a look at the intensity forecasts here. Our initial forecasts here in the western and central Gulf of Mexico do a very good job of capturing the intensification of Milton from a tropical depression through to a major hurricane, both in terms of the rate of that intensification, that rapid intensification that was observed, and to somewhat lesser extent, the peak in intensity. We weren't quite able to reach the Category 5 peaks in intensity with these early forecasts. Most of those approached into the Category 4, almost Category 5 range here. But as we move to later and later forecast cycles, the lack of having data assimilation within our forecast system becomes more and more apparent. The dots here are the 0-hour intensities from those successive forecast cycles, and we just aren't able to, with the GFS cold start initial conditions, match that. So we have the model constantly trying to play catch up in those first 24 hours to the observed intensity. At these higher intensities on the 8th and 9th, we do see fluctuations over 12 to 24-hour periods in the simulated intensity, and these are due to eye wall replacement cycles that the model was explicitly predicting within its forecasts. And I'll show an example of that in just a moment. The better constrained problem of decay near and after landfall was pretty well predicted by the forecasts, and then these continue out after Milton had become post-tropical. So in terms of that overall forecast verification, again, the orange bars are our MPAS forecasts, very small track forecast errors at all forecast lead times, better than the NHC official HAFS A and B and GFS from 36 hours onward. Of course, small sample size notwithstanding. For intensity, the lack of data assimilation early on shows up very acutely here in the 12-hour forecast. Then by 24 hours, we're already catching up, and then our 36, 48, 72, and 96-hour forecasts, even out to 120 hours, are pretty good for Milton's intensity here. So taking a look at that simulated eye wall replacement cycle, this is from the October 7th forecast. So this is a 48-hour forecast here, depicting a primary eye wall here near to the center of this smaller eye, and then a nascent secondary eye wall at somewhat larger radius. Relatively compact wind field here, 64 knot winds, extending out about 100 kilometers across the storm, 34 knot wind, radius 75 nautical miles, 150-ish kilometers. Then just 18 hours later, that inner eye wall has collapsed, replaced by that larger single outer eye wall with a much larger expanse of both 64 knot and 34 knot winds, over doubling of the 34 knot wind radii. So kind of toggling back and forth just to illustrate that. Quite dramatic structural transformation seen with Milton, not unlike that which was seen in observations. So for our future plans, we're working to backfill our missing forecast cycles for both Debbie and Francine. Francine, we only missed the first 3 forecasts, so those should be fairly straightforward for us to complete out the forecast period. And then Debbie, we have a larger number of missed forecasts. We're about a third of the way through those. Our off-season, we plan to focus on process-based evaluations of our MPAS forecasts. We really want to dig into the forecasts and the available data, especially for those storms that had recon flights, to evaluate our physics, to assess what improvements are necessary to further improve our forecast skill. And so anyone who might be interested in collaborating with us on this work, we'd love to have those discussions with you. We hope to be able to support real-time cycle data assimilation with MPAS and JEDI for next year's hurricane season, although there's a lot of open questions as to what data we will be able to assimilate. If I were to make an educated guess, I'd say it'd be a fairly standard, fairly basic data assimilation capacity for 2025, hoping to build to more complexity for subsequent seasons. And in terms of our domain extent, we recognize we're pretty limited, especially for the large-scale influences on track by the relatively small domain size. So we're considering both regional, but with a much larger extent, covering North America and the North Atlantic for next year, as well as an initial capacity for global, whether that be course resolution or something variable resolution going to storm scales in the Atlantic Basin. And so with that, I'll close there. Thank you, and I look forward to questions later in the session.
Thanks, Craig. So we are back in in-person talk. I believe next speaker is Tim Marchuk from GFDR. He is going to talk to us about the GFDR T-shirt real-time experiments.
Okay. All right. Good afternoon, everyone. So yeah, I'll be talking about our performance of our GFDL, T-Shield and Shield real-time runs from this past hurricane season. But first, I want to acknowledge the other members of our group who have helped with this: Quinn, Lucas, Linjong, Matt, Jamway, and Alex. Next slide. Oh, it might work. Just the forward button. Okay. Okay, so for those of you who are not familiar with our SHIELD family of models, SHIELD stands for System for High Resolution Modeling from Earth to Local Domains. It's an FV3-based system. SHIELD is our global model, 13-kilometer global model. T-Shield is also a global model, 13-kilometer resolution, but it has an additional 3-kilometer high-resolution nest placed over the Atlantic domain to allow for two-way interaction with the global domain. Some of the differences between the two configurations are highlighted in blue. Some of the major ones include vortex initialization is included for T-Shield for systems that are at least 60 knots initial intensity, and also deep convection. T-Shield has deep convection in the global domain, but it's turned off in the high-resolution inner nest. Both models start from the GFS. There's no additional DA that's done. Changes for 2024, there were none for SHIELD as we're preparing for transition to a higher resolution 6.5-kilometer real-time SHIELD. For T-Shield, Quinn added changes to the mixing length formulation in the PBL scheme and also changes to the surface layer scheme. And both of these were meant to address intensity forecast and wind structure concerns. So for the rest of the talk here, I'll start off with track verification, then get into intensity and wind radii, and then TC rainfall for our landfalling storms. And I don't think I'll have time to get to the genesis. So these are life cycle track plots from T-Shield. The color shading is not intensity. It indicates the age of the forecast. Brown are the oldest forecasts, all the way up to green at the later end of each forecast. So the forecasts for Burl were pretty good forecasts, although there's some left of track bias, especially in the western Gulf of Mexico. Debbie, also fairly good, but some trouble making that left-hand turn in South Carolina. Ernesto had, again, pretty good tracks, but a few stray tracks left of track. Forecasts for Francine were pretty good. Helene, the tracks were excellent. Also for Kirk. And for Milton, some of the early forecasts were a little bit left of track, but then pretty good the rest of the way. Shield's very similar. Left of track bias for Beryl. Some cross track error with Debbie. And then good track for Francine. Excellent tracks for Helene and Kirk. And then also pretty good tracks for Milton as well. So looking at verifications here, these are late models that I'm comparing here. So I did two different sets, one with ECMWF on the left, and then in order to double the number of cases without ECMWF on the right. And so on the left, the T-Shield errors are shown in red, and Shield is in blue. And so for the whole season, the T-Shield errors were right up there with GFS, with low track errors through 4 and 5 days. The Shield errors were close, comparable to T-Shield through 72 hours, and then there's an increase in error at 4 and 5 days. Without ECMWF, it's a pretty similar picture, although with the added number of cases, the GFS has a little bit more of an edge over T-Shield at 4 and 5 days. Breaking that up into cross-track error and a long-track error. Cross-track error on the left, T-Shield had very low cross-track error, shown in the red with the red line there, and Shield had higher cross-track error, shown in the blue line. But for a long-track error on the right, Shield had the lowest long-track error, and T-Shield was about in the middle there. It's interesting to note that all of the models this season had this, when you combine the two of those, had this slow left of track bias. Okay, intensity and wind radii. Again, these are life cycle intensity plots. And I'm just going to be talking about T-shield here. So for Bill, the forecast generally had the picture right, but you can see by a lot of forecasts there being underneath the black best track line, really failed to get up to that peak intensity for all of the forecasts. Debbie forecasts were pretty good. There was kind of a mixed bag, really. Some of the forecasts got that peak intensity and some of them missed it. Forecasts were pretty good for Francine and Helene, but then there was some trouble for Kirk and Milton, in particular missing the peak intensity for Kirk and then specifically missing the rapid intensification for Milton. So looking at the intensity forecast verifications, and here I'm showing T-shield with HAFS A, HAFS B, and HWRF. So T-shield's intensity forecasts have improved from where they were last year. It's at least in the same ballpark with HAFS A and HAFS B. Last year it was well outside of that range with higher errors, and that's also evident in the biases that are shown on the right figure there as well. And when I stratify this by initial intensity, this box on the left, the two plots in there, weak storms and strong storms, and I chose that 60 knot cutoff because that's where we start to use the vortex initialization. So for the strong storms, the initially stronger storms, T-shield intensity errors are comparable to those of HAFS A and HAFS B throughout the full 5 days, but it's a much different picture for the weaker storms on the left there. The errors are larger and they grow at a faster rate. I think that's due to a combination of cold starting with no VI from the GFS, and then also poor performance for rapid intensification cases that's shown on the right here with this RI performance diagram. Looking up the y-axis here, HAFS B had the highest probability of detection. T-shield had the lowest, and then looking across the x-axis, HWRF had the lowest number of false alarms, and T-shield had the highest. Looking at wind structure, R34 verification here, there were large improvements in T-shield's R34 errors for this year compared to prior years. Again, looking at the red line for T-shield errors, had the lowest errors at 3, 4, and 5 days. And it can be seen, the improvement can be seen in the biases on the right plot for the red line, which is T-shield. Initially, negative bias kind of drifts up towards the 0 line, drifts more positive, where in prior years, that bias had been increasingly negative throughout the forecast. So I think some of these changes that Quinn added for the surface layer, the boundary layer, have made an impact here. TC rainfall. So unfortunately, with the substantial number of landfalling hurricanes this year, it gave an opportunity to do this verification with a comprehensive number of cases here. And so I'm looking just TC rainfall for landfalling cases. And I did a little bit differently this year. In the past, I've normally looked at cases that start just close to landfall, 6, 12, 18 hours. But I wanted to, 5 minutes? Oh yeah, okay. But I wanted to back it up to see, is there more skills for warning further in advance? And so what on this figure, where you see those tracks start, that's the first cycle that I used for each of these cases in doing the verification. So looking at Helene here, the stage 4 observed precip is on the left along with the best track. These are 72-hour rainfall total starting from 0Z on the 25th. And then the two global models, SHIELD and GFS, are on the top on the right, and then T-shield, HAFS A and HAFS B on the bottom. And so even from this 0Z cycle on the 25th, this is about 2 days in advance of the onset of flooding, most models were predicting these extreme totals in the Appalachians in North Carolina, Tennessee, Western South Carolina. But in particular, T-shield and HAFS B, did a really nice job of picking out some of those, the details of the extreme rainfall in Western North Carolina. So looking at some verification stats for rainfall, this first one on the left here is kind of just like a gross bulk statistic, where just looking to see, did the model simply get the right amount of water dropped in this area? And here, limiting it to within 600 kilometers of the best track. And so we just compare that with each of the models, and we get a bias for, an average bias. So out of this, all of the models display a small to moderate under forecast bias. With HAFS A had the smallest bias, about 3% too small. HAFS B and T-Shield were about the same, 5% under forecast bias. And GFS and Shield were pretty comparable to each other, about 10% under forecast bias. On the right is something a little different. This is a track relative analysis where it helps to minimize the impact of track error, where we're comparing the observed precip in these bands along the x-axis. They're 20-kilometer wide bands, and it's totally accumulated rainfall in these bands. And we compare that with the forecast model and the forecast precip surrounding the forecast track. So the observed track here, observed precip is shown in black. So for T-Shield, that red profile is slightly less than the observed, out to about 200 kilometers. The Shield profile in blue is a bit weaker than T-Shield's. And HAFS B overproduces rain in the core region, but then outside the core, its mean profile matches the observed very well. So last rainfall plot here. Here, trying to get an idea of the distribution of some of these rainfall amounts within 600 kilometers of the best track. And so again, we add this up over all the cases, and we can get a couple of meaningful stats out of this. The text box on the left talks about the median in the distribution of the rainfall. And that median in the observed is 3.8 inches, and the T-Shield profile perfectly aligned with that. All the other models were slightly skewed towards weaker amounts, with Shield skewed the weakest to the left. We can use the same plot. The details are difficult to see on this at this scale, to look at extreme rainfall, which of course is important for flooding. And so here we focus on the 95th percentile in the observed profile, and that is 11.3 inches for the observed.
Kim, 2 minutes.
Thanks, Zach. So T-Shield and HAFS, their profiles almost perfectly match the observed for the distribution of extreme rainfall, and all the other models underpredicted the extreme amounts by some small amounts. I don't have time to talk about the genesis. If you want, please see me after, or you can check out the slides after. But because we run T-Shield at every cycle, not just when there's a storm, it gave us the opportunity to see how well our high-res model did on Genesis. Okay, so to summarize, the first and third here are the most significant. Very strong track forecasting performance for T-Shield. And then the third one, significant improvements were seen in the R34 forecast for T-Shield, both in error and bias. That was a significant improvement over prior years. Some improvements were seen in the intensity forecast compared to prior years, but we're still lagging a bit in RI performance. And then also, it was good to see actually very good TC rainfall performance from T-Shield and Shield, as well as the other models as well. All right, thank you.
Thanks, Tim. So our next speaker is Jia Peng from EMC. He is going to talk about HAFS-based ensemble prediction on cloud. Jia, go ahead.
Okay.
Give us a second to load the online.
Oh, okay. So yeah, before the break, we're gonna have a last two talk. Oh, sorry. So we're gonna have a two talk. So I'm gonna focus on the scientific part, and the Salah is going to present how the Microsoft Azure team So they did a great job to support this project in the past few months.
It's not showing up either. We did the exact same thing as last time.
I know. Same.
Online, we don't have it.
I know.
That would work it out. I'll share it online.
Oh, okay. Sorry, Jody.
It's okay.
We tested all of these things.
Yeah, everything was working at the break,
Everything was-
and now, it's the nature of the way things like this go. Yes. The transition from Google Slides to PowerPoint just causes some weird issues on the computer.
Practiced much.
You're not sharing the slideshow mode. This one, yep, that one. Nice talk, Jackie. Thank you.
Oh. Okay, now we can start now.
Yeah.
Okay, yeah. So I'm going to talk about the housing symbol in cloud. So last year we ran the housing symbol in AWS. So this
We can't. The machine's locked up that controls the TV and the screen.
so it's working now.
It's working remote, and we're gonna have to have the inset video for right now. The machine that's sharing the screen is locked up, so it's got the presentation up there. We just can't make it screen right now. So you're good.
Good to go.
Yeah, it's just gonna look a little funky.
Okay, so this is online. So the first one, I'm going to talk about the issue or cavities in last hurricane season for the housing symbol. So the second one, so as for this hurricane season, we have lots of changes, new configurations, and also I'm going to show some products. The last one, that's the verification for the whole season. Next slide. So in 2023, so we run 20 member plus one control. So our initial data generated from the 30 member GFS. So we didn't do any recenter process because we just grab it from the global ensemble. So for this year, we have the 30 member. So this means we don't need to recenter either. So that's automatic. So okay, the second one, we have the initial intensity bias in last hurricane season. So in 2024, we added 2 jobs, try to deal with try to merge, okay, the original house vortex with the basin domain. So the third issue is we have the under dispersive for the track intensity. So we added another SPP for the perimeter ocean surface roughness. So we try to make the uncertainty or spread bigger. So you'll see this verification we do. So some of those issues. And the next few slide I'm going to next slide please. Talk more detail about it. So from the table you will see compared 2024 to 23. We have member changes from 20 to 30 member, and resolution change, and also macrophase from GFD to Thompson. For the ocean model, so we have last year we only have a high count, so this year we're going to have mom 6 and high count. So as we run house A and B, so both to make some difference here too. So there's something hide there. Okay. So so that's why I mentioned it. So except the SPB.
Stochastic physics.
Oh, really? So that's good. So we add another SPP, try to make the intensity spread bigger to solve the under dispersive of the intensity forecast. So for the initial and the boundary condition, so it came from the 30 member plus one control from the GFS global and that's half degree group together, and the ocean indication from R top. So yeah, another uncertainty we try to identify. Oh, thank you so much. Okay,
There.
go here.
There, that way you can see it.
Yeah, okay, yeah, thank you, right. So
Or
I got
I didn't have it on. Okay, you got it?
Yeah, I can put it here. So it's okay. So yeah. So another uncertainty we're trying to figure out is how much for the initial vortex, including the position and intensity. So for the location or position of the vortex, we have like a random perturb half degree. That's the location. For the intensity, we have among the 31 member, we have a 21 member apply the analysis half A vortex or half A less dominant field. So 6 member with the 6-hour focus, that means the previous cycle, and the 4 member from the previous two cycles, that means 12-hour forecast. So this means that we have the uncertainty from the location and also the intensity, including structure. Okay, so we run the 2 cycles. So 0, 0, and 12 day. On the right side, that's okay, sorry about. So on the right side, that's the domain. We cover the whole Atlantic and also the Gulf of Mexico. So for the 1 member, we use 4 nodes, 704 cores. On the other is HPV4 loads. So for the 31 member, so we have 124 at least to make sure we can run smoothly for the whole ensemble system. So all the data is everybody can access. So anywhere you have internet, so and it's free. So we also have a website you can take a look. So I can go next slide, or you go. Okay, so here, so to construct the 2024 HAFS symbol, we have the HAFS A and the B physics parameter. So here's the table. So I'm not going to go into detail about it. So we have the horizontal damping and the surface layer parameter and the PPO scheme, and even the deep convection, and also the coupling. And we have HICOM and MOM6. So we make some difference. So we have the 50 member use the HAFS A package, and another 50 member with the HAFS B. That's for the physics difference. Okay, next slide. So for the stochastic physics, so we added an extra SPP. We perturb the ocean surface roughness. So as we perturb this ocean roughness, we can generate the what is the CD and CK. So that surface is changing coefficient for momentum and heat and moisture. So those black curve, that's the current operational profile. So we perturb in the orange or other color, okay, except the black. So that's the perturbation. So there's a 2 line in the bottom show how we make the perturbation. Next slide. So now I'm going to talk about the products. So yesterday and many talk about the hurricane Hurricane. So you can look at this here. I want to show one cycle. That's for the 24th 0 day. So you can look at the ensemble mean chart, right? So you first you look at red compared to the black. Black is that's the best chart. Is the location match very well. Also, you can look at the ensemble. All other members cover very well. So the envelope is in good shape. So also another one, you can look at the as I cannot look, okay. Look at the number 3, the black and the red speed. That's the landfall time and location. So this means that we predict the rain 3 days earlier for the landfall timing and the location. And then on the right top, that's the wind speed. So maximum wind speed, you can look at it as half of the members reach to the category 3, category 4, and some close category 5. So that means a major hurricane is coming. So also look at the system of pressure. So we also have lots of members deepening enough to reach the observation. So the next slide, please. So yeah, this plot show you the horizontal. That's the 24-hour intensity change. Yeah, the vertical, that's the probability. So you can just focus on the orange bar and the red bar. So that shows the remarkable intensity changing in the next 3 days before landfall. Yeah, that's not good. So now we come to the product for the PCOPF. That's a okay. So that's for the same cycle. The day 4. This on the left. That's a day 4. 1 day, 24 hours. PCOPF. That's rainfall greater than 1 inch. So on the right, that's from the observation. That's yeah, something covered. That's fine. That's for the CCPP, the observation. So you can look at our PCOPF. So the orange color, just look at orange color, match the observation very well for the location. So that's for the PCOPF. Next slide. Yeah, that's just that. We also have the hurricane structure, wind probability, and those. 2
minutes.
Whoa. Okay. How good. Okay. So then I'll okay. So this is for the location for the chart. On the left, you can look at the yellow compared to all other color. So the chart is much better than all other determinants, including the HAFS A and B. Okay, next slide. And for the intensity, so again, the same color. So look at the yellow curve compared to all other color. So those intensity error is very close to or even better than the determinants. But there's one big deal over there, that's a bias. So the HAFS symbol has a big bias between 24 to 72 hours. That will be our bigger work next year. We're going to solve this. Yeah, next slide. Yeah, this here shows a symbol that's a error on the spread relationship. So on the left is 2023, on the right that's for 2024. So you can look at for the track on the top right. So we lower the track error, but we increase the track spread. It's perfectly match. So for the intensity, so we did increase the spread of the intensity, but as I said, from the first 2 days, the intensity will just grow too fast. So our job in next year, we just make it slower to grow. So they are going to match the spread. Next slide. So, okay. Here, so I'm going to talk about how important one is for the VA and the VI and DA, and also how to identify the initial uncertainty. So you can look at it here. So the one test is we use only 6-hour focus vortex. We do nothing. We don't have a DA. We don't have VI, any process. Just purely previous like a 6-hour focus vortex. You can look at most member go west. There's only one member has a U-turn. On the right, so we have a combination. So different water apply different inhalation. You can see some member go east have a probably U-turn. So that's a difference or initial uncertainty show up here. And the next slide. So you can look at something from the beginning on the right. Two plots show the initial uncertainty of PDF has a better, and a better match from the observation. On the left, so the 6-hour vortex make a little stronger from the beginning. So that's my last slide. Next. Yeah, so the summary. So as I mentioned in the beginning, so we added those like SPP, and also we have the HAFS A and HAFS B physics difference. So we make the spread and error ratio much better. So the second one, that's we merge the operational vortex, HAFS A vortex into the basin domain. We remove the initial elective intensifier. So we have work to do. That's the third one. That's how we reduce intensity error bias in the first 3D. So future plan for the 2025. So as we didn't run the DA and VI in cloud, so maybe we can do in next year. And also, so most of our bias is come from the resolution. So that's why we try to either run the multiple storm movingness or increase the horizontal routine from 4 to 2 kilometers. May solve or reduce a lot of negative bias. And we consider, as Andy already showed, the HAFS XB. So the different physics, the TDX include. So we have some physics diversity or stochastic SPB. Of course, the last one, so we need a more computing resource. Okay, that's all I have.
Thanks, Jiayi. So the last talk of this session will be given by Royal Verghese, and he's going to talk about NOAA and Microsoft collaborations on cloud computing.
We're running. I'm sure
You better do.
Maybe if I unplug.
There we go. Okay, I got it.
You got it?
I got it out of the stuck window.
Yeah, if you share your screen, let's see what happens.
I won't. I will wait for him to be ready, unless I can
You-
start.
Yeah, go ahead and share
You
from
can try
yours,
sharing.
Okay.
Yeah.
and we'll just do it that way. Just because don't want it to get stuck in another transition window.
Got it.
Thanks, Roy. Appreciate it.
No problem.
You know those Microsoft products.
Oh.
This PowerPoint locked us up.
We were gonna-
You went there.
Yeah, I could have gotten more personal, but.
I thought it was a Google Meet.
Yeah.
Yeah, but what
That's-
locked it up was the Windows 11 with PowerPoint.
I see.
Uh-huh.
You guys don't play nice.
All right, let's see, share. Is it working?
Yeah, but it didn't, you're sharing
I'm in presenter mode.
but it didn't share that one. It shared the other screen.
Which is strange.
Yeah, that's one of the problems we were having is when you put it in the slideshow, you have to go back into the meeting and then share the slideshow window that comes up.
Okay,
So you have to put it in slideshow first and then alt tab over to the meeting.
and I will do.
Hi, Solar, how are you?
Hi, everyone.
That.
Good to see you.
I hope my voice quality is coming over fine.
You're coming across well.
About now.
You have to do it slideshow first and then tab back over to the meeting.
Which is what I did first.
And
time.
it didn't work.
That's what I was having trouble too today.
Oh,
That's
man.
exactly what was working this
Stop
morning.
sharing.
Happy to, especially my husband.
Oh, yeah, that's right.
I did it in this.
How about we do the?
Say just share the PDF version instead of the PowerPoint.
Yeah, that's
version.
fine. That's
That might work better at this point,
Yeah. Oh, that's-
only because then we don't have to keep changing programs as much.
Right.
Yeah. Let's try.
We're gonna try to share the, unless you got it to work.
Let's see. We'll see. One last try.
Okay, hold
Oh,
on.
there you go. Looks like.
All right,
It's working this time.
Hey.
Oh, well, then, perfect.
Look at that. Well, good afternoon. That's how technology works, right? Roy Varghese with Microsoft, and I'm joined by Solar Adili, my colleague. He's at another location. I wish both of us could be here together, but we decided to divide and conquer. So first of all, thank you for the opportunity to chat, and we're going to go, since we lost some time here, we'll go fairly quickly. The nature of the conversation here today, you heard from G about the work we did. Thank you, G. But this conversation is about, to some extent, why we are doing what we're doing. You may know Microsoft from PowerPoint and Windows, but we're a little bit more than that in terms of the work that we do. And we see this work with NOAA as coming together of leaders in a couple of different domains. We respect the work that NOAA does, especially Weather Service does, over the last 150 years, doing weather forecasts in such a way that's protected life and property. For the last 50 years, only third of that life is what Microsoft have been in business. And the last 10 or so years, we've been very focused in providing leadership in AI. And you all have been hearing about it the last year or so. But that work is coming out of a history of research we have been doing. And this is an opportunity to come together and do something that's important. And just to set the context here, Microsoft as a company deploys a supercomputing cluster almost every week, the size of, say, your WCOS. So I'm not saying that to brag. I'm saying that to say, this is what we do. A part of our business that you probably never heard of. This is what we do. So we have the operational rigor, like you have the operational rigor to get up and get those collect those observations from Cat 5 hurricanes, flying the planes. We can't do that. Well, we can deploy supercomputers, and we are one of the largest users of it. So we understand the implications of using for operational needs, as well as we are making it available for our customers, which means that we can invest heavily. And you probably heard about the billions of dollars we're investing in this space. And we have a global footprint. And that's important in the context, from my perspective at least, where NOAA is going to go, right? You want to continue to dominate and provide leadership in this arena, and having a global scale infrastructure and a partner with a global scale infrastructure that can support you is important. And what does that mean? Just one example, like our AI supercomputer that was in the news the last couple of years. We went in 2020, we had 10,000 GPUs. Last year, we came out publicly, said a portion of it, 14,000 GPUs landed in the top 3 in the world. And the actual system is a lot bigger than that. And we intentionally don't want to disclose that for business reasons. And this is to set the stage in terms of our experience in this arena of building the infrastructure to do this work. So why does it matter? And this is where I want Solar to chime in and take it away, Solar.
I appreciate it. Thank you for this opportunity. Sorry, I'm dealing with a little bit of a wireless connectivity issue. We're in the space weather building in Boulder today, and it's always a pleasure to be connected to NOAA. It doesn't matter from where. So the why it matters for us. Well, first and foremost, the great work that the team is doing here is very much aligned with the Weather Service's top 10 capabilities that they're looking for with probabilistic IDSS, and doing this in an ensemble-based probabilistic forecasting method. And it is very much aligned with the cloud capabilities, because it's addressing surge computing that you need for a small period of time. And we have what we're providing here is a partnership that aligns the science, the infrastructure capabilities and search computing, plus a vast amount of artificial intelligence and HPC expertise that we've built as a major, enterprise ourselves in collaboration with others, either our own Microsoft Weather side of the house, which folks might not know a lot about, but if you see the weather forecast in any of the billion plus Windows machines out there down in the corner, it's produced by our own weather team here, along with other Weather Nation and Weather Enterprise partners like the Met Office and others. So we bring a vast amount of lessons learned and collaboration expertise that we can bring to the fold. We also, as Roy mentioned, been in the HPC business for a very long time, and we do have we're part of the top 10 of the fastest supercomputers in the world, and also bringing what we bring to the table is all of those expertise that come from building those HPC systems and rolling them out, and along with our Microsoft research capabilities, all of the big group of PhD folks that do research like yourselves and publish on, and be able to put all of these teams and expertise together to achieve a ambitious goal here. And this year for us mattered a lot because it was the second experience for the HFIP team running their model in the cloud, and we really had our eyes on doing this in an operational resolution in the cloud this year. So we actually, and that's the reason behind that is for us to help pave the path on envisioning a hopefully a near future where these models, as they get more complex and they require more computational power from physics side, and in the future potentially in the AI side, to be able to see that vision coming more and more into reality with these experiments that we did together and pave that path for it. Roy, if you don't mind advancing. So with that in mind, we came into conversation basically talking about what are the elements that we can provide and put on the table, and what can we do in a different and in a more closer to operation manner. So from a compute standpoint, the team collaborated to bring integration with the Genoa X VMs, which was the latest available at the time. And with that effort, which was not Microsoft only, an effort, a collaborative effort between us and the key partners here, to achieve 22% more access to cores with 33% less nodes required, which means it optimizes the cost more as you get to the higher end compute capabilities. And we also invested to employ the latest storage and networking capabilities directly into the partnership that NOAA and Microsoft and ParallelWorks and team have to make sure those capabilities are built in and available to all of NOAA for this purpose and for any other future need that they might have. And it is because of our heavy HPC presence that we do have we do certain things differently, where, for instance, with the interconnectivity of these nodes, having the InfiniBand capability there by default for all of the fleet was an important point here. And I'm going to be a little bit quicker here moving forward, but it's important to also call out that incorporating our knowledge and bringing programs and available capabilities across NOAA with NOAA Open Data Dissemination and the integration that they have with Microsoft Planetary Computer, and ultimately be able to direct investments from our Microsoft HPC Global Black Belt, Roy and team was a key factor here as well. And we also replicated that with our other key partners like GDIT and ParallelWorks to make sure all of us are cohesively working towards that goal.
Hey, Solar, we have 2 minutes left.
Okay. just very quickly, we also realized that in order to hit the ambition of running at the operational level, we need to invest and put our own skin in the game as well, which is, it was both from a collaboration manner with the key partners and injecting capabilities into their software, and also providing some additional funding to the HAFS project in order to help with the fiscal year sort of switching and the ability for the team to be able to hit the goal that they had for the resolution and the amount of compute needed for this work. I want to highlight the most important thing that made this happen is having that one team mentality and the collaboration that enabled this work from engineering side of the house, from the management of the tasks and capabilities from all sides involved, and from the leadership of NOAA, Microsoft, GDIT, and Parallel Works. We all worked as if we were part of the same team, and we were all there where things were not working optimally or needed additional attention, all the way from our engineering and engineering from every party involved, and to move this forward. So I want to applaud that partnership first and foremost. That's the key ingredient here that allowed us to achieve success. So what's next? We did hit some ambitious goals this year. We hope to continue our work in partnership to be able to increase resolution even further. As GIE mentioned, be able to do the DA and vortex initialization in the cloud as well, pass these capabilities along, and hopefully see a future where whether there's potential for incorporating GPUs and AI capabilities or optimizing further, to see that future where these cutting edge capabilities are there year round for development and implementation and operation for the betterment of our nation.
All right. Thank you so much.
I do want to just add real quick that we gave time to Solar and Roy to come talk about what they did to help us this year, because they were extremely instrumental in meeting with us very often, not only with the HFIP program, but with EMC, HRD, and all the NOAA OCIO level people at Parallel Works and General Dynamics IT that are part of the OCIO contract to really help us out. And the $500K that they granted really did make a huge difference at getting us not only more efficiency on the nodes we use, but actually being able to increase our science a lot over the first go round, which of course that wouldn't have happened without all the help from Amazon AWS last year. So thank you guys. And with that, we'll open up the questions for the session.
Yeah, we have 10 minutes for questions. Please raise your hand in person or virtually.
I don't. With Frank, are you online with a question? I didn't see a hand. No? Okay. You went down?
Yeah.
All right, Ben, here you go.
Yeah, hi, Ben Woods with the Weather Program Office. And I was just looking closely at what was planned in the future. Correct me if I'm wrong, but I think the last 2 years, including this year, the HAVs on the cloud didn't really start until August. Is that right? So is there any plans to cover more of the season?
I can actually answer part of that. Part of that is because that's when the real-time experiments start. We do the setup in June and usually early July to get things going. And then it goes from there. And when we have downtimes in the season, retro runs of previous storms are done. So we don't actually miss the time. We just have to have something to start with to get it ported over and evaluated. But if there's anyone from EMC or any of the other real-time experiments who wants to answer that, or VJ wants to say anything.
So yeah, I think Aaron already answered the question, but the point is the prime season that we wanted to test all these innovations is between August and October. And that's where the focus has been for the all real-time experiments that you have seen today. And that gives people to get ready and then roll up their sleeves and set up these experiments, because we are not running 24/7 operations. It is mostly testing innovations that cannot be tried on operational machines. So That's the main reason.
Frank Marks. So the question that comes to mind is we're really getting a lot of help in producing product. How are we getting that product in HC, and how can we utilize the resources we have to make their lives better?
So right now, this is an experimental product, so it's.
I understand,
Yeah.
but what I'm looking at strategy down the line, this partnership grows. Is NHC have a say in any of this? Are they giving us feedback? Are they seeing any of these products? Is it going into the funnel top and not getting out?
Yeah, I'm heading to Wallace so he can answer, but it does make it into model viewers as well as other aspects.
Yeah, I was just gonna say, in the case of the HAFS ensemble on the cloud, it's experimental. We're treating it like it's experimental. We've been working with JAI and EMC team to grab the data from I was gonna say AWS, sorry, Microsoft folks. Grab it from Azure and test the data flow, test the post-processing. John Martinez has been building some stuff. So we're building the capabilities so that we absolutely could, yeah.
Get people together who want to work with ensembles and
Yeah.
bring them.
We haven't done as much, others from NHC can correct me, we haven't done as much with like T-Shield and some of the other models.
And I just want to add that we're actually a couple of steps ahead of where we normally would be with the ensemble, because we were able to work with the NOAA OCIO last year to get cloud. So we had real-time run of this at least a year ahead of what we were expecting. So there's still a long way to go, but we're making good progress. And like Wallace said, all the other real-time experiments are either in HOT or in other similar ways to be looked at for their evaluation too.
Yeah, I'd like to see a Tiger team form and put together to do this.
Understood.
I don't have a say anymore, but I'll raise my hand and I'll.
Do you volunteer yourself to be a free volunteer Tiger team lead?
I can lead a Tiger team. You just give me the people and I'll point them. I'm interested in rainfall. I want to work with Tim.
Well, if you go to the EMC model viewer and look at the output from this ensemble, you will see the rain swap information there. It actually did quite well.
And Frank, it's like we do have a Tiger team. We have Jai and myself at EMC, and also Microsoft, and also the Wallace at NHC.
The personnel from GDIT that support OCIO were heavily involved, especially Raj Panda, on porting code and getting these things up and running.
Certainly, that's an idea. It's a way to address some other concerns we raised before, to help us get it quicker to the forecasters for real-time interactions and feedback.
Philippe Pappen, I'm one of the hurricane specialists. So I have looked at some of these tools like the HAFS ensemble. I looked at, even though it's experimental, if it's up on the web and there's a way for us to view it in operations, we have PCs where we're accessing the web and other products through additional portals versus our traditional platforms like AWIPS and ATCF that we're using to make the forecast. But really the end goal here should be, I kind of like the idea of maybe having like a hot, sort of similar to a hackathon that happened a couple of years ago for operational data sets that we now have in AWIPS that we're looking at on a regular basis. Maybe we should do something very similar for, different, HAFS ensemble based or other HAFS versions that are experimental, have a similar type of hackathon and see what kind of products can be transitioned to AWIPS, because that's our primary platform that we're accessing data visualizations and being able to use that and transitioning over to making the forecast in ATCF.
For reference for those online, Frank gave his thumbs up.
So I really want to take this opportunity to also ask the community to think big when we come next year to 2025 hurricane season. Apart from the hurricane ensembles and the routine HREX experiments that we are running on JET, there may be additional computing available. We have new machines now. The C6 Gaia has come in. We have potentially a RIA GPU machine. And we also will have a HERA replacement, URSA, coming online next year. So there will be huge computing available for the first time that in the recent past that we can think big now. And I really want people to think of how to take advantage of these machines. And apart from the help that we get from Microsoft and Azure and other people, I think we need to really plan big. And I'm really looking forward to having these discussions prior to the next hurricane season.
Yeah, I probably will switch gear a little bit. I have a question for Tim and Matrix talk. It looks to me, especially for the track forecast, JFDL T-shirt is doing a great job this year. I know HFS is doing a great job. So what might be the improvements you guys put in their T-shirt give us a very good track forecast?
So the improvements that Quinn put in this year were actually intended specifically for intensity and wind structure forecast. So I don't think that what he added this year really made a difference for the track forecast. The track forecasts were very good last year too. I do think that one of the things that is that may be helping our track forecast is that we don't use convective parameterization in the inner nest. And for good or for bad, I think that is making a difference.
Andy, do you want to respond?
Yeah, one thing to add to that, I'm guessing part of the other reason for that is that you still have the large 3-kilometer nests based on the global. So you're getting a large area where you don't have the convective parameterization, where you have better resolution. Because we saw that back like the old versions of HAFS when we were running the global nest. I think the ensemble results were showing the same thing, much better track with that large, even at 4-kilometer. So that's something to think about as we get more and more computer power, do we think about these like basin scale type things, instead of just at least with the track problems.
Yeah, can I make a comment about T-shields? This is more spender enjoying retirement. But, one of the things too, as Tim said, we don't have deep convection. And also one of the things that Kuhn had done from the very beginning is that we do retain shallow convection, but we've made some clever modifications with the entrainment and detrainment with the shallow convection. And I really think that's come a long ways to make the impressive track performances with T-shield. So it's partly not just, turning off the deep convection, which I've always kind of advocated, but, there were problems with that, but we played around with the shallow convection and included that. And that really, I think, is the thing that's been helpful to us.
All right, thanks, Morris. I guess we're already 2 minutes over the time. And okay, one more question. Okay.
Yeah, I won't take long. I've been sitting here listening to last few days. Great science conversations here. I've only been at Microsoft last 3 years, and what I see is the big gap in terms of how private sector executes on imperfect information versus I was in government I was in NOAA for 12 plus years in terms of how we process when we're in government and move from research to operation. I think the Tiger Team idea is another idea in terms of incorporating parallel operations to really field test, because government has a lot more to lose with inaccurate information than a private company like us who run our models every hour and push results, data out and our products out. Whereas you have a lot more rigor to it. But there's no right or wrong. I think experimentation and collaboration with industry partners like us who are willing to work with you, I think would be a great effort. And I'm sure there are others like us willing to step up.
I hear what you say, this is Hendrik, but the reason why we as NOAA are slow is because we have a public-private partnership where our private partners do not want us to take risks. So it's kind of a interesting two ways of looking at it.
Thank you, Hendrik. And with that, we'll close out this session. We're going to take our full break, so we'll start at 3:34 with the next session.